As we draw closer to December 19th, the date when 3I Atlas will make its nearest approach to Earth, the scientific community is gearing up for a major observation event. Hundreds of ground-based telescopes, along with the powerhouse Hubble and James Webb Space Telescopes, are standing by to capture the highest quality data possible on this mysterious visitor. However, independent observers have already stumbled upon something that technically shouldn't exist. Reports coming in from two different countries using entirely different sets of equipment have confirmed a startling anomaly. A sunward-pointing jet extending from 3I Atlas. This jet has maintained a stable orientation for over 48 hours, appearing in both Thailand's rotational gradient filters and Italy's natural light captures. This isn't just a dust tail being swept back by solar winds or a simple trick of perspective. It is a narrow, coherent plume aimed directly at the sun. Observed across multiple sessions and through various processing methods, the structure didn't just persist, it grew brighter and longer between December 7th and December 9th, all while maintaining a perfectly fixed axis without any wobble, drift, or signs of breaking apart. Standard physics tells us that solar pressure should be pushing material away from the sun at speeds of 400 kilometers per second. Yet this feature is doing the exact opposite, pushing toward it. What makes this even harder to ignore is the state of the nucleus itself. In every frame, the core remains perfectly compact, showing no distortion or structural collapse. Instead, we see an asymmetric brightness enhancement that completely violates the standard physics of how comets are supposed to behave. If you've been waiting for undeniable data on 3I Atlas, this is the moment. This is no longer just a processing error, it is a cross-verified, reproducible structure that needs a real explanation. The data from Thailand's MPC observatory is particularly compelling because the comparison between December 7th and 9th removes any lingering doubt. On the 7th, the rotational gradient filters showed a small, faint sunward feature that was almost hesitant, barely extending past the nucleus. At that point, you could have dismissed it as background noise, but by December 9th, 48 hours later, using the same equipment and methods, the structure had essentially exploded. It didn't disappear or scramble, it amplified. The sunward plume stretched further, became sharper, and split into two distinct components. The main jet doubled in length, while a counter feature on the opposite side strengthened, creating a clear V-shaped geometry. This 48-hour comparison proves that the direction and axis of the jet remain perfectly aligned. If this were just random noise, and the orientation would have shifted, if it were an artifact of the image processing, different sessions would have shown different angles. Instead, the feature stayed locked onto the sunward axis and grew in intensity. This indicates a real physical source that is becoming more active, not just a degradation of the image. The fact that the plume length doubled suggests that material is being actively expelled along a very specific path. We even see improved symmetry with a primary plume and a counterjet, which suggests a stable bipolar outflow. This stability is where standard comet models really start to fall apart. Typically, features on a comet don't stay still. Dust fans rotate as the nucleus spins, and gas jets wobble as vents turn toward or away from the sun. Even the viewing angle should shift as Earth and the comet move relative to each other. Yet, this structure holds its line like a fixed engine. Two different nights, two different images, but the same direction and an even stronger signal. Further analysis of the Thailand data through a triple panel approach, grayscale, inverted contrast, and color-enhanced mapping further deepens the mystery. In standard grayscale, the nucleus looks like a tight, focured point with no signs of breaking up. If you only saw this, you'd think 3 Atlas was just an ordinary comet. However, the inverted grayscale, which is designed to highlight subtle structures or fragmentation, reveals that the core is incredibly compact with no signatures of spreading or instability. Then there is the color-enhanced map, where the entire picture changes. The outer halo lights up asymmetrically with the brightness stretching toward the sun rather than away. In a normal comet, the intensity is highest in the opposite direction of the sun because of the solar wind. Here, the reverse is true. This combination of a stable core and a sunward-facing brightness map is a massive red flag. If the comet were fragmenting, it would look messy. If it were venting normally, the tail would dominate. Instead, we see real energy being pumped into the sunward region, suggesting an active thrust rather than passive sublimation. This evidence becomes practically bulletproof when you look at the observations from Tony Scarato in Italy, working from a completely different part of the world with different optics and filters. He documented the exact same structure. His raw, natural light exposures show a faint forward brightening in the same sunward direction as the Thailand data. When he applied the gradient filter, the structure snapped into focus a central tight nucleus with a narrow, bright jet shooting directly toward the sun, while the comet's tail behaves normally, pointing away from the sun as expected. This sunward feature remains focused and unwavering. When we summarize what we are seeing, several key points emerge. First is stability. The axis has held constant for over 48 hours, which doesn't happen with natural wobbling jets. Second is growth. The structure grew longer and more defined over time. Third is the direction. It is aimed directly at the sun, which would require a force stronger than the solar wind to maintain. Fourth is cross-verification. Independent observers on different continents captured the same thing. Finally, there is the integrity of the nucleus, which stays perfectly intact even as material strings away. Natural explanations are starting to require very specific, almost improbable conditions to work. Perhaps it's a jet at a very specific angle or a unique trajectory of dust particles. But when you combine all these factors, the stability, the growth, and the cross-verification, the simplest explanation is one that many are hesitant to voice: something inside 3I. Atlas might be generating controlled thrust. If this were a probe, we would expect to see exactly this: directional thrust for course correction, a stable orientation regardless of rotation, a compact structural core, and consistent behavior regardless of where it's being watched from. While this isn't the definitive claim of artificial origin, the data is pushing us toward possibilities that mainstream astronomy is often unwilling to consider. The longer the silence remains regarding these sunward jets, the stable axis, the more that silence feels like avoidance rather than science. Whether it is an unusual venting angle or something far more deliberate, these observations demand our attention.